Section 1, Basic of Lab Investigation. We have two main purposes that connect the concepts of limiting reactant, stoichiometry, and percent yield. The first purpose is to predict the limiting reactant in the reaction between sodium bicarbonate and acetic acid, which produces carbon dioxide, water, and sodium acetate. In order to find the limiting factor, we will use stoichiometric calculations and dimensional analysis. We then use the limiting reactant to calculate the theoretical yield of sodium acetate for the varying amounts of sodium bicarbonate in 3 different trials. Afterwards, we calculate the percent yield of sodium acetate in each of the 3 trials. In this experiment, we needed 3 beakers weighing both acetic acid, sodium bicarbonate, hot plate, weighing scale, cylinders, hot hands, and goggles to conduct the experiment. For this experiment, we hypothesized that as the amount of sodium bicarbonate increases, the greater the percent yield of sodium acetate. Regarding safety, it was required to wear goggles throughout the whole experiment and use hot hands to carefully deal with the beaker on the hot plate to avoid any burning. In addition, for disposal, we carefully disposed of the sodium bicarbonate into the garbage bin after the experiment was completed.
This is section 2, the experimental portion, and Sophia Tarasenko, Natalie Tarani, and Kushi are all going to be talking in this part. So for the experiment, we only had 3 group members, so we could only do 3 trials using 0.10 grams, 0.15 grams, and 0.20 grams of sodium bicarbonate. The purpose of this lab was to see if increasing the amount of sodium bicarbonate will affect the amount of sodium acetate produced. There were 3 trials, each one using a different amount of sodium bicarbonate. The set amount of sodium bicarbonate was added to the acetic acid, both being the reactants, and this mixture was stirred and heated to successfully separate the products, CO2 and H2O, from sodium acetate. Then we found the mass of the sodium acetate for each trial by subtracting the mass of the empty beaker from the mass of the beaker with the sodium acetate. So the data that each of the trials collected were the mass of the empty beaker, the mass of the beaker with the acetic acid, the mass of the beaker with a mixture of sodium bicarbonate and acetic acid, and the mass of the sodium bicarbonate. We weighed each step of the way, just in case if we need the masses later on, and it's always better to have extra data rather than not enough. So we wanted to do extra.
Hi. Okay, this is my data table, and it correctly represents our hypothesis, with the first reaction producing the least amount of sodium acetate of the 3, and it produced 17 grams. And then this suggests that increasing the amount of sodium bicarbonate will in turn increase the amount of sodium acetate produced.
And this is my data table that presents the masses of everything we weighed. I noticed a trend that my reaction produced more sodium acetate than Natalie's reaction did. So increasing the amount of sodium bicarbonate has been shown to increase the amount of sodium acetate.
Shown is the data table that represents the 3rd trial with 0.20 grams of sodium bicarbonate. The amount of sodium acetate produced was greater than trial 1 and 2, with 0.22 grams of sodium acetate being produced.
Our hypothesis was that within a reaction, if the amount of sodium bicarbonate increases, the percent yield of sodium acetate will increase as well. Our data suggests that the validity in this statement being that when 0.1 grams of sodium bicarbonate was used in the reaction, 0.17 grams of sodium acetate were produced, and when 0.15 grams of sodium bicarbonate were used, 0.19 grams of sodium acetate were produced. We ran our experiment again to increase the soundness of our conclusion, and we found again when 0.2 grams of sodium bicarbonate were used in the experiment, 0.22 grams were produced of sodium acetate were produced in turn. Now, we did run our experiment a few times and let our beakers heat for around 35 minutes, so we feel our data is valid as it could have been, considering our precision throughout the experiment. Now to move on to the limiter chart. There we go. To the limiter chart, we see that our first 3 trials had the sodium bicarbonate as their limiting reactant because they were fully consumed in the reaction. However, when we tried 0.3 grams of sodium bicarbonate, acetic acid became the limiter because it was the fully consumed reaction. For percent yield, we found that for 0.1 grams, for the 0.1 gram portion, it was 157%. This was our calculation for the actual outcome and our anticipated outcome. For 0.15 grams, it was 172%, and for 0.2 grams, it was 157% again. So I guess you could say that our experiment could have been more accurate. Maybe we could have been more thorough about the sodium bicarbonate and it being poured into the beakers. but I think we did a pretty good job.
So for the first question, they give you the grams of carbon monoxide, so you use stoichiometry to convert this amount of grams into moles. Grams cancel out here and here, leaving you with moles of CO, and we get 0.58 moles of CO gas. For part 2 of question 1, this is a limiting reactant question. So we're going to convert the grams of the reactants into the grams of the products. To see which one is going to be the limiter, it's honestly whichever one produces less solid iron in this case. And in this case, iron 3 oxide produces less iron. As we can see, it produces 10.76 grams of iron, and CO, carbon monoxide, produces 21.53 grams of iron. So that's much more than this. And for part 3 of question 1, it was honestly another stoichiometry question, and you're going to convert the grams of the iron 3 oxide into the grams of the Fe. And these grams cancel out, leaving you with moles, but then these moles cancel out, leaving you with these moles, but then these moles cancel out, leaving you with grams of Fe. As you can see here, we used mole ratios because we have 1 mole of Fe2O3 to 2 moles of Fe. So we use a mole ratio here, and then we know that 1 mole of Fe is 55.85 grams of Fe, and then you multiply the top, you multiply the bottom, and you get 10.76 grams of Fe formed in the reaction.
Hi, okay, so I'm going to do the second post-lab question. This one is about combustion analysis, so it's from a while back, but let's see if I still remember. Okay, so we have the hydrocarbon burns completely producing 5.91 grams of water and 7.2 grams of carbon dioxide. So we have to find the empirical formula of the hydrocarbon. So to do this, first we have to find the number of moles of carbon and the number of moles of hydrogen within the reaction. So we do 7.2 grams of carbon dioxide, and then 1 mole of carbon dioxide would be 44 grams. So we multiply that by 44 grams of carbon dioxide to cancel out the grams. And then within that 1 mole of carbon dioxide, there's 1 mole of carbon. So to get the moles of carbon, we have to have this top number, or the numerator type be that just has to be on top because we want to be in moles of carbon. Okay, then for moles of hydrogen, it's basically the same exact thing except with H2O, because we know that we have 5.91 grams of water when produced in the reaction. So we do that over 1, and then we multiply that by 18 grams of water, because that's what 1 mole of water is. And then there's there's supposed to be there's supposed to be a 2 there, but it's 1 mole of H2 is over 1 mole of H2O, because we want to be in moles of H2. There's supposed to be 2 there, but it's okay. And so we get 0.328 and 0.6 or 0.164. So we always have to divide by the lesser number. So we're dividing by 0.164, we're dividing both of them, and then we get CH2, because 0.164 divided by 0.164 is 1, and 0.328 divided by 0.164 is 2. Okay, so then we have to calculate the mass in grams of oxygen required to complete the combustion of the sample. So first I started by balancing. There are, in the balance equation, there are 2 CH2s and then 3 O2s, and then that yields 2 CO2s and 2 H2Os. So obviously we have 3 moles of O2, so we'll put that over 1, and then we have to cancel out the moles, so we do 1 mole of O2, and that's 32 grams, and then we multiply out, and we get 96 grams of O2 required to complete the combustion. Thanks, bye.